At the last station, we discussed that Darwin saw organisms that were similar yet distinct. On various Galapagos Islands, Darwin observed finches with beaks that were slightly different in shape and size. But why did this happen? This can be explained through natural selection. In different habitats or locations, different traits are favored. For example, in areas where seeds are abundant, ground finches need thick, strong beaks to crush those seeds. In forested areas, finches need long, skinny beaks to be able to grasp insects from the trees. However, it is also possible for an environment to change. Adaptable populations are more likely to survive and pass on their traits to offspring. For example, a population of moths who was primarily white-colored became dark-colored because of pollution that changed the trees they lived on to a darker color. The moths that were originally dark were able to camouflage and pass their dark trait along to the next generation. We are going to be simulating this example to see how this moth population was affected over their environment being changed. We are going to start off with 100 moths, 90 white moths and 10 black moths on white paper to represent their environment. This will be referred to as the parent generation. Remember, before pollution affected the trees, they were covered in white lichen. This means that the moths that were light in color were able to successfully camouflage, survive predators, and pass on their traits to their offspring. Because of this, the white or light color was favored. However, it's important to note that the white allele was actually recessive, while the black allele was dominant. Remember, alleles are different versions of a single trait and are responsible for variation within a population. In our example, the black allele will be represented by a capital B, and the white allele will be represented by a lowercase b. This is important because we need to do some calculations to determine the colors of the moths in our next generation, or the offspring of our parent generation. To do this, we need to determine the frequency of the homozygous recessive genotype. This will be represented by Q squared. We discussed the alleles that make up genotypes in our last lab, but in case you've forgotten, in order to express a recessive trait, you need two recessive alleles. In this case, our recessive allele is represented by the letter Q, and since we need two of them, it becomes Q squared. To find Q squared, we need to divide the number of white moths by the total number of moths in our population. Since this is our first set of calculations, we'll do this together. So we're going to divide 90, which is the number of white moths, by 100, which is the total number of moths, which gives us 0.9. Make sure you record this number on your data table, as well as all of the numbers we discuss coming up. Q, which represents our white color, is 0.949. Multiplying that number by 100, you get approximately 95 beads. P, which represents our black color, is 0.051. Multiplying that by 100, you get approximately 5 beads. So I've gone ahead and counted these beads out and added them to the cup here. I'm going to be mixing the cup around and then randomly pulling out 2 beads at a time to determine the genotype of this first generation. While I do this, I will record the corresponding genotypes on the data sheet, using a capital B for black and a lowercase b for white. I'm going to repeat the process twice so that there are a total of 100 moths in the first generation, which is the same number of moths that were in the parent generation. Once I determine all 100 genotypes, I'm going to be using the paper moths to express their phenotypes. So let's get started. Alright, so we have now determined the number of genotypes for our first generation. Remember, that's the offspring of our parent generation. So in our first genotype, which is going to be homozygous dominant, represented by 2 capital B's, We actually did not have any representatives for that genotype. And this should hopefully make sense if you think about it. We only had 10 black beads out of a possible 100, so to pull 2 out of those 10 at the same time was very unlikely. Now, for the second genotype, which is the heterozygous genotype, represented by a capital B and a lowercase b, we had 10 representatives. Now again, this should make sense to you. We had 10 black beads in the cup, and they had to either be pulled with another black bead or a white bead. Since we already discussed that there was no homozygous dominant, that means all of the black beads must have been pulled out with another white bead. So 10 total heterozygous genotypes. And then moving on to our last genotype, that is our homozygous recessive, represented by 2 lowercase b's. Of course, you hopefully have realized that there are 90 left over, so there are 90 representatives that have this homozygous recessive genotype. Now, let's discuss the phenotypes. So again, our black is our dominant allele. So that means the homozygous dominant and the heterozygous genotypes will translate to a black color. So again, we did not have any homozygous dominant individuals, and we have 10 heterozygous individuals. So that means we will have 10 black moths. And on the other side, we had 90 homozygous recessive individuals. So that means we will have 90 white moths. This is exactly the same as our parent generation. While we didn't know the exact genotypes of our parent generation, we now know the genotypes of our first offspring generation. So now we're going to use those numbers to calculate the individuals for our second generation. So before we move on to the second generation, let's simulate that change of environment that we talked about before. Remember, this actually happened. Pollution caused trees to go from a white color, caused by the lichen that colored them, to a dark color because of pollution. Once their environment changed, now the black moths could easily camouflage and thus survive to reproduce, while the white moths were easily picked off by predators. So I'm going to change the environment, and we're going to assume that half of our white moths are going to be eaten by predators before they can reproduce. However, we're going to keep all of our black moths, since they will probably be very successful at camouflaging in this new environment. Okay, so now we have our new environment and our new population. So you can see our black background represents these trees that were affected by pollution, and we have our 10 black moths remaining, but now we only have 45 white moths. Again, the other 45 were picked off by predators. So we're going to use these new numbers to calculate our values for P and Q and determine what our next generation, our second generation, is going to look like after this environmental shift. So I'm going to calculate those numbers myself, and while I do that, I'll give you a chance to calculate them on your own. And then in just a moment, we will check our numbers and make sure we're all on the same page and move forward with creating the next generation. Okay, so let's go over the numbers for our second generation. If you haven't yet finished your calculations, pause this video while you do so. The value you should have calculated for Q squared is approximately 0.818. You should have obtained this value by dividing the number of white individuals, which is 45, by the number of total individuals, which is 55. Now to calculate the value for Q, which is our recessive allele frequency, you are going to take the square root of 0.818, which is approximately 0.904. And finally, to calculate the value for P, which is the dominant allele frequency, you are going to subtract 0.904 from 1, which gives you 0.096. To determine the amount of beads to place in the cup, you should have multiplied both P and Q by 100. This gives you 10 black beads and 90 white beads. Remember, the beads represent the alleles, not the color of the individuals themselves. We are going again allow the individuals to reproduce until there are 100 members of our new generation, and that means we need 200 alleles total. So I'm going to be repeating the procedure with the cup twice to reach that 100-member population. So let's get started. Okay, so now that we've randomly finished choosing beads from our cups, we can go over the genotypes for the third generation. So this time we actually did get one individual with the homozygous dominant genotype, again represented by two capital Bs. This time we had a higher chance of pulling out two black beads at a time since there were more black alleles in the cup. Moving on to the heterozygous genotype, we had 19 individuals who ended up randomly having that genotype. Again, remember, these individuals will have a black phenotype because black is the dominant trait. So that gives us a total of 20 individuals that will be black. Moving on to our homozygous recessive genotype, we have 80 individuals that express this genotype, and they are going to have a white phenotype. Again, because white is the recessive trait, you need two alleles to express that color. So I'm going to go ahead and reset our environment to reflect those new conditions. Okay, so now our population is back up to 100 individuals comprised of 20 black moths and 80 white moths. But again, the white moths stand out against their new polluted environment, and so they are going to be subject to predation. So we are going to assume that 50% of these white moths get picked off by predators before they can reproduce. So I'm going to remove 40 of the white moths from our population before we get started on our next generation. Alright, so now we have an environment that represents the moths that are going to be able to reproduce and form the next generation. So again, that's 20 black moths and only 40 white moths. So now you want to perform the same calculations we've been doing again. So you want to find the values of P and Q, and then use those values to determine the number of alleles, or beads, that we're going to put in our cup to randomly assign the genotypes and phenotypes for our next generation. So go ahead and do those calculations, and then I will be back in just a moment to go over them with you. Okay, so let's go over the numbers for the third generation. Again, if you haven't finished your calculations, pause the video until you do so. You should have calculated 0.617 for Q squared. Again, that number is obtained by dividing the number of white individuals, which is 40, by the total number of individuals, which is 60. Then you want to find Q by taking the square root of Q squared, which should give you a value of approximately 0.817. Using that number, you can now find P by subtracting 0.817 from 1, and that will give you a value of P, which is 0.183. Now you can use both your P and Q values to figure out how many beads are going to go in the cup, or how many alleles are available for the next generation. So again, multiplying each P and Q by 100, you get approximately 18 black beads and 82 white beads. So I'm going to be placing those in the cup. Again, we're going to allow our individuals to reproduce until we have 100 in the population, so that procedure will be repeated twice. Alright, so I've finished randomly pulling beads out of the cup, so let's go over the genotypes for the third generation. So starting with our homozygous dominant, we have 3 individuals expressing that genotype. They are again going to express the black phenotype. We have 30 individuals expressing the heterozygous genotype, and again that means they will also express the black phenotype. And lastly, we have 67 individuals expressing the homozygous recessive genotype, which means they will also be expressing the white phenotype. So I'm going to reset our environment to affect those changes, and then we'll keep going from there. All right, so here's what our population looks like for generation 3. We have 33 black moths and 67 white moths. Now again, these white moths in the polluted environment, they stand out. So some of them are going to be impacted by predation before they can reproduce. So I'm going to remove approximately 50% of these white moths. This time it's an odd number, so there will be a little bit of rounding. And then we will use our surviving population to determine our numbers for generation 4. So from here on out, you're going to be calculating the alleles available for each generation on your own. I will provide you the genotypes and phenotypes of each generation, so you have those numbers to use for your calculations. We are going to continue this demonstration until we flip the population so that there are only 10 white moths as opposed to 90 black moths, so the opposite of what we started. If you haven't already, there's a place on your handout to record a hypothesis of how many generations that will take. So I'm going to, again, go ahead and remove the moths that have been subject to predation, and then we will get started on generation 4. Okay, so I have removed 34 moths, or I should say 34 moths were subject to predation before they could reproduce. So now we actually have an entirely even population. So we have 33 white moths left that were not exposed to predation, and we have 33 black moths that were able to camouflage and remain unseen by the predator. So again, we're going to move into our 4th generation. This time I'm not going to give you those allele numbers. You'll be responsible for calculating them yourself, and let's see what happens with our moths here. Alright, so I have calculated values for P and Q as well as the amount of available alleles for our next generation. I have gone ahead and put those beads into the cup and then randomly drew them out two at a time, and here is our resulting generation. So again, this is our 4th generation. So we had 9 individuals that were homozygous dominant, which means they will express a black phenotype. We had 40 individuals that were heterozygous. They will also express a black phenotype. And lastly, we had 51 individuals with a homozygous recessive genotype, which means they will express a white phenotype. So I'm going to reset our environment here to reflect those changes. Alright, so here is our new population, but again we have our predator, and the predator can very easily see our white moths. They don't camouflage. So 50% of our white moths are going to be killed by the predator before they can reproduce. So I'm going to remove 26 white moths, which will leave us with 25 left for reproduction. Okay, so I have now removed all of the white moths that experienced predation. And here we have our population that will be actually reproducing and producing our 5th generation. So again, calculate your P and Q values. I'm going to let you do that on your own. And then I'm going to randomly pick beads from the numbers that I calculate to put into the cup, draw them out, and then I will give you the genotypes and phenotypes for the 5th generation. Okay, so I have calculated our P and Q values and the alleles that will be available for our next generation. I put those beads in the cup and randomly drew them out 2 at a time until we had a 5th generation of 100 individuals. So let's go over the number of each type of genotype. So for the homozygous dominant genotype, we had 19 individuals, And remember, they will have a black phenotype. For the heterozygous genotype, we had 46 individuals. They will also have a black phenotype. And lastly, for our homozygous recessive individuals who will have a white phenotype, there were 35. So I'm going to start rearranging our environment here to reflect those changes so we can see what our new population looks like. All right, here is our 5th generation. Just like all of our other generations, these white moths stick out against the polluted background. So half of them are going to be picked off by predators before they can reproduce. So I'm going to remove approximately 50% of our white moths. Again, 35 is an odd number, so there will be rounding involved. Okay, I have removed 18 of the white moths from our population, again about 50%. So now we have our reproductive population that will breed the next generation, which is going to be the 6th generation. So again, calculate your P and Q values and the number of alleles that will be available for that generation. And while you're doing that, I will do my own calculations and randomly pick beads out of the cup to figure out the colors of our new generation. Okay, let's go over the numbers that we calculated for our 6th generation. Again, we used the P and Q calculation to determine the available alleles, and then randomly chose 2 beads out of the cup at a time to figure out the new members of our population. There were 30 homozygous dominant individuals randomly chosen from the cup. Remember, those individuals will express a black phenotype. And then we had 50 heterozygous individuals chosen, which will also represent a black phenotype. And lastly, we had 20 homozygous recessive individuals chosen, which will express a white phenotype. So I'm going to reset our board here to reflect our new population, and then we can go ahead and calculate the numbers of our 7th generation. Again, we will calculate P and Q to determine the available alleles, and then choose 2 randomly from the cup at a time to see who's in our 7th generation. Just like our other generations, we are going to assume that the white moths are very easy for the predators to pick off and that we're going to lose 50% of them before they can reproduce. So since we're starting off with only 20 white moths, I'm going to remove 10 of those, so our next generation will only have 10 to begin with. Okay, so here is our population that is going to be able to reproduce for the 7th generation. So again, calculate your P and Q values to determine the available alleles, and then we will discuss the members of our 7th generation. Let's go over the numbers for the 7th generation. Using the numbers you calculated for P and Q, and using that to determine the available alleles for this generation, I pulled out 2 beads at a time randomly from our cups. From that, I determined 44 individuals to be homozygous dominant, expressing a black phenotype. In addition, there were 46 heterozygous individuals, also expressing a black phenotype, and lastly, just 10 homozygous recessive individuals expressing a white phenotype. So I'm going to reset our environment to express those changes in our population. So now that we only have 10 white moths left, I'm going to end our demonstration. Hopefully this helped you see how the environment can play a role in evolution and determine what traits are passed along. You can also see how closely tied evolution and genetics are to one another. One quick note, these moths that we used in the example only live for 1 year. So if our simulation happened in real life, that means we would see these drastic population changes in a matter of only 6 years or possibly less. This should show us that it's important to take care of the environment because anthropogenic effects like pollution can drastically impact plants and animals.